Okay, so actually this page is about the RL circuit, so you can see somehow the same circuit as the previous page. And actually, it just tells you the solution of this circuit. I will not tell you why it will be like it yet, because after finishing this chapter, I will tell you how to solve the differential equation in a set, at least the constant coefficient differential equation in a systematical way. Yeah, so here I can just tell you that what is the differential equation, because we already tell you for this inductor, it should have something like this is VL. So this VL should be like L times di dt. Okay, the current going through the whole loop should be I. Okay, and then for this one, this is VL. So this VL should be like I times R. Okay, and then maybe you can just assume this is a ground. Okay, so you start from this point and then going for the loop. Okay, so this is 0, and then this is negative, positive, so it should go up. Okay, so we have a E. This is going up, and then starting from this will be going down, because RLC should be something like consuming the power. Okay, so it should be like going down, which means that we can just put it on the right side, or maybe we can just subtract this V out. Okay, you can consider this is positive, this is negative. Okay, so here we have a positive side, and then this is positive, this is negative, so we should subtract V out, and then also here plus minus. Okay, so we should subtract VL, and then going back to this point Z, so it should be 0. Okay, so here we can just plug in the thing like E equals VR plus VL, which should be VR is I times R, and then VL is L di dt. Okay, so we can see this is actually a differential equation with constant coefficient. So we can just like dividing L on both sides. So we should have this is di dt plus dividing L on both sides. So L and L cancel. We will have R over L and then times I, and then equals E over L. Yeah, so this is the differential equation, first order constant coefficient differential equation. Okay, so the solution of this one should be that one. Okay, later on I will tell you why it will be like that. So far you just try to believe it is correct. Okay, at least you can see this is R over L. Okay, and then we have L over R. So you can see this is like I over tau L. This is called the time constant. And then we have E over R, and then 1 minus, this is an exponential function. And then we assume that we just start from t equals 0. Okay, we don't consider the negative time. Okay, so t is a positive value. Tau L is this one. L over R is still a positive value. So this is a negative value in the exponent. Okay, exponential to a negative value should be less than 1. Okay, and then you can consider the smallest one when t equals 0. Exponential to negative 0 should be 1, and then exponential to negative infinity should be 0. Okay, exponential function is like something like this. This is exponential to e to x, okay, or e to t, This is the time. Okay, it's something like this. This is 1. Okay, so 1 minus this thing should be a positive value. This thing is between 0 and 1 when t is larger than or equal to 0. Okay, so this is a positive value. Okay, so you can see I But actually, this is VR. VR is I times R. R is a positive value. So we multiplying R to there. So actually, VR is nothing but e times 1 minus exponential to t over tau L. Okay, so here you can see we start from 0 because e to minus 0 is 1. 1 minus 1 is 0. So we start from 0. And then we try to increase up to e, because when t is large, this one will be 0. So this term will be 1, 1 minus e will be e. So it will settle to e, Okay, so what is the physical meaning of the tau L? Tau L is called the time constant, which means that when t equals tau L, when t equals tau L, this is 1. So which means that e to negative 1. E to negative 1 is, I'm not sure, 0.368 if I remember correctly. You can check it using your calculator. If I remember correctly, this is 0.368. 1 minus 0.368 is like 0.632, okay? So which is around here. Okay. So what does it mean? I don't know. Actually, I mean that this one will not be equal to e precisely. Okay, it only approaches e when t is very large. But in engineering sense, when t is larger than maybe 3 tau L or 5 tau L, if t is larger than 5 tau L, then we will just ignore this error between this one, because exponential to negative 5 should be very small. You can check it using your is small. And then in engineering sense, usually we will just ignore this thing. So which means that when t is larger than 5 tau L, we will say that VR is approximately e. Okay. So that's the meaning for the time constant. Okay, and later on I will let you know how we can derive the solution of this differential equation. But as much as we have this one, yeah, which means that we start from 0. We start from there is no current in the circuit, and then at t equals 0, we try to connect. Maybe we can consider there is a switch at t equals 0. It just close the circuit so that it start to have current. And as I mentioned in the last hour, I mentioned that the current should be continuous. The current of the inductor should be continuous, which means that at the beginning, the I should be 0, and then it start to increase. So at this moment, I is continuous, but VL is not continuous, because you can see this is the derivative. VL is the derivative, L di dt. Okay, you can see at this point, this is not differentiable. So VL at this point is not, it's not continuous. When t is smaller than 0, VL should be 0. But when t is 0 plus second, then it suddenly jump to a positive value. Okay, I don't really sure what is that value, but actually we can recalculate it. But this is out of the scope of this semester. So but at least you know the current of the inductor should be continuous. Okay, so but actually so we may still use this equation, but later on I will tell you why after finishing this chapter. So here is a sample problem. Yeah, so here it says a figure shows a circuit that contains 3 identical resistors. So these 1, 2, 3 resistors are identical in value, okay? And then with resistance R equals to 9 ohm, 2 identical inductor with inductance L equals to 2 millihenry, and then ideal battery with E equals to 18 volt. Oh, this is 18 volt. Okay, what is the current I through the battery just after the switch is closed? Just after the switch is closed. Okay, so before the switch is closed, because this is open, okay, so I is 0 when t is smaller than 0. T is smaller than 0 second. Okay, there is no current, no current, no current. Okay, so no current for this part also. Okay, so for when t is smaller than 0, okay, there is no voltage, no current. Okay, all the way 0. Okay, so I0 minus should be 0. This is I0, maybe I1, I3. 0 minus should be 0. 0A, 0A. Okay, no current going through. So it should be continuous. It should be continuous. So which means that when the switch, after the switch is closed, which means that this is t equals to 0 plus second. Okay, so this should be I10 plus. Okay, this is continuous. Continuous for the current of the inductor. Okay, for these two paths. Okay, I3 0 plus is also 0. It's also 0. It shouldn't be any. But for this resistor, the current doesn't necessarily to be continuous. So yeah, so after the switch is closed, it should be like something like this. Only the middle one. So this is I2. This is I2. I1 and I3 this is just like we have a resistor, but this one is still open at t equals 0 plus. T equals 0 plus. And this one, R is here, and this is still open. This is still open at t equals 0 plus. So we can just ignore the left path and the right path, which means that so this is I should be I2. So I should be E over R, which is 18 over 9, which is 2A. Okay, so this is for the first case. So you need to keep in mind that the current of the inductor is continuous. So at t equals 0 plus, which means that the time after, just after the switch is closed. Okay, so there shouldn't be current going through this path or this path. Only current going through the middle path. Okay, for the second question, what is the current I through the battery long after the switch has been closed? After the long, so which means that here, long after the switch has been closed, which means that t tends to infinity, or t is much larger than 5 tau L. For this one, tau L is not L over R. It should have a different expression, but yeah, we just assume there is a time constant, and if this time is much larger than this one, okay, much larger than this one, and then t tends to infinity. Okay, when t tends to infinity, we will consider that I is a constant. I is a constant. So VL equals L di dt. As much as I is a constant when t is very large. So I is a constant, which means that di dt should be 0. So when t tends to infinity, VL should be 0. VL should be 0. It's just like a short circuit. So which means that when t tends to infinity, the circuit will feel like this L become a wire, and then R, and then here R, and then R, this is also R, and then L become a wire. There is no voltage drop across the current when t is very large. Okay, this is E. Okay, so this is I, and then when T is very large, the inductor is just still like a wire. So we have a 3 resistor in parallel, which means that the R equivalent should be like R over 3, which is 18 over 3, which is 9 over 3. 9 over 3, which is 3 ohm. So I should be 18 over 3, which is 6A. Okay. Yeah. Okay, so this is a sample problem about the inductor characteristic. So for A and B, we only consider T equals 0 plus and T equals infinity. So if you like to consider any T between, you need to seek for the differential equation and then you try to solve it. But we'll learn this later. So here is an other sample problem. So it says a solenoid has an inductance of 53 millihenry and a resistance of 0.37 ohm. If the solenoid is connected to a battery, how long will the current take to reach half of its final equilibrium value? So I will be like E over R 1 minus exponential to negative T over tau L, something like this. Okay, which means that the equilibrium value is this one. Actually, we don't really care about what is this value, as much as we would like to know how long does it take to the current to reach half of its equilibrium value, which means that this thing should be 0.5. Should be 0.5. Okay, so we don't care about what is E, what is R. Okay, which means that we should have 1 minus exponential to negative T over tau L should be 0.5, which means that exponential to negative T over tau L should be 0.5, and then we can just make it positive and then take the reciprocal on the right side. Okay, which means that we can take lateral log on both sides. So we have a lateral log and exponential to cancel each other. We have a T over tau L equals natural log of, this is 2. Okay, so finally we have T equals tau L times natural log of 2. Okay, and then tau L is nothing but L over R, natural log of 2. So we can just plug in the value. L is 53 milli, and then R is 0.37. So we have 53 times 10 to negative third power over 0.37, and then natural log of 2. So this number is 143.2 millisecond. Yeah. Sorry. 143 is this value. So multiply by natural log of 2. So multiply by natural log of 2 should be 0.1 second or 100 millisecond. Okay. Okay, should be like this. Okay, so next we talk about the energy stored in a magnetic field. Okay, in chapter 25 we talk about the energy stored in the electric field. So if you still remember, the expression is like UE equals 1/2 CV squared. Okay, so this is still a duality. Okay, you can see this is UE, this is UB. 1/2 are the same. And then for the electric field is stored in the capacitor, stored in the E field. Okay, the E field is generated by the capacitor. Here, the energy is stored in the inductor, or stored in the B field. The B field is generated by the inductor. Okay, so C and L. And then here, for the capacitor, we talk about the voltage or the potential difference, V. And then here, for the inductor, we talk about the current. So these two are derivative to each other. And then if you really need to derive it out, so dUB will be P equals IV, and then the V of the inductor is like L di dt, and then we can just do UB will be integration of a dUB. Maybe we can just put it prime here, so that this UB and this UB can be distinguished. Okay, so we can just put in this thing into here. So we have a IL di dt and then dt. Okay, so dt cancel each other, and then finally we have a IL di. L is a constant, so integrating, so it is like L integrating a di, maybe just put it prime, I prime, and then integrate from 0 to I. Okay, so this is I squared over 2, so we have I squared over 2 times L, so this is 1/2 Li squared. Okay, yeah, so so here we have an other sample problem. So it says a solenoid has an inductance, okay, with the same value, and then 0.5 ohm. If a 12 volt EMF is applied across the coil, how much energy is stored in the magnetic field after the current has built up to its equilibrium value? Okay, so it is easy, which is like I equals E over R for the steady state, because the general expression should be like I equals E over R 1 minus exponential to negative T over tau L. But it said that for the equilibrium value means that this one is 0. So it's nothing but E over R. Okay, which means that it is 12 volt over 0.35. So this is 34.38. Okay, so we can just calculate UB by 1/2 Li square. So 1/2 times 53 times 10 to negative third power, and then times I square is 34.3 square. So this number is 31 joule. Okay, so for part B, how after how many time constant? Okay, will have this equilibrium energy to be stored in the magnetic field. Okay, Okay, as much as UB is 1/2 Li square, which means that if we need to have half of the equilibrium energy, which means that UB half should be like 1/2 Li half square, and then this one should be half of it. 1/2 of it should be equals to this one. So which means that we should have a 1/4 Li square equals 1/2 Li half square. Okay, so after cancelling all the thing, I half should be 1 over square root of 2I. Okay, so, and actually the expression should be like I equals I 1 minus exponential to negative t over tau L. So in this case, as much as this one should be I have should be 1 over square root of 2i equals I and then 1 minus exponential to negative t half over tau L. T half over tau L. So I and I can be cancelled. And then we have exponential to negative t half over tau L equals 1 minus 1 over square root of 2. Okay, we just move this one over, move this thing over. Okay, we will have this one on the left side. On the right side, we will have 1 minus 1 over square root of 2. And then we just take the reciprocal on both sides, so it becomes a positive. And then we take the reciprocal here. So take the reciprocal here will become square root of 2 minus 1, and then square root of 2. And then we can take natural log on both sides. So we have t half over tau L will be natural log of square root of 2 over square root of 2 minus 1. Okay, we only need to know how many time constant, so we just leave it on the left side. So actually you can still calculate t half, the value of t half, but here we need to know how many multiple of tau L it is. Okay, so it is nothing but natural log of square root of 2 over square root of 2 minus 1. So this number is nothing but 1.23 times. 1.23 times. Okay, so next we talk about the energy stored in the magnetic field again. So we will have something called the energy density, just like what we have for the chapter 25. We have energy density for the in the electric field. Okay, so here we try to verify this expression using the solenoid. Okay, so assume we have a solenoid here. So this is the current, and then we have the UB stored in the inductor. The UB should be like 1/2 Li squared. So we have Li squared over 2. UB, so UB, small UB should be UB over the volume. So the volume for this solenoid should be like this is the length multiplying the cross-section area, A. Okay, so A times L will be the volume. Okay, so this volume, this thing should be A times L. So we have UB over AL, and then UB is 1/2 Li squared. So we have Li squared over 2, and then AL here. Okay, so we just try to rearrange things. So we have capital L over L. So this is inductance. This is the length of the inductance. So actually this is nothing but the inductance per unit length. We have already derived it previously. So L over L is mu0 n square A. And then the remaining thing is I square over 2A. I square over 2A putting here. And actually, this is a solenoid. So we have a B equals mu0 in for a solenoid. Which means that we can just have I equals B over mu0 I. And then putting this thing here. Okay, so here we have B over mu0 n rather than I. This is n. Okay, so B over mu0 n and then quantity square over 2A. Okay, so we can do all the cancellation. So let's see. This A and this A can be cancelled. And then this n square and this n square can be cancelled. This is n square in the denominator, so we can be cancelled. And then mu 0, and then this is a mu 0 square, so it is partially cancelled. So we will have mu 0 at the bottom, and then this is 2, so we have 2, and then also we have b squared, like this. Okay, so the final expression is ub equals b squared over 2 mu naught. And then if you still remember for ue it is 1/2 epsilon naught e squared. Okay, so the idea here is to change e to b, change e to b, and then change epsilon naught to 1 over mu naught, so that this mu naught go to the denominator. Okay, so this 2 is also a duality. Okay. So next we talk about something called the mutual inductance. Mutual inductance, you can consider it is a transformer. So in the world, there are 3 types of transformer. This is the first type. It's called the 变压器. Okay, there are 2 other transformer. One is the 变形金刚 transformer. Okay, the Optimus Prime. Okay, yeah, and the third one is the transformer in the AI. Okay, I don't know what is the Chinese name for the transformer in AI. Usually they just call it transformer. The transformer can be useful for the natural language processing. So so recently, the ChatGPT is very famous. So chat, you know, chat is just chat. Okay, what is GPT? G means generative. P means pre-train. T means transformer. Okay, so transformer is useful for that purpose. So GPT means 生成预训练的 transformer. Okay. But actually, that is not this transformer means. So we altogether have 3 types of transformer. So this one is 变压器. Okay, 变压器. Okay, so you can see here is 2 coil. So one primary coil and the secondary coil. So it depends which one you try to connect a battery or try to connect the source. So for this one, actually these 2 with the same transformer. But here for the first one, we connect N1 to the battery. So we call this one the primary coil, this one is the secondary coil. But for this one, we connect the source for N2. So for this case, we call this one primary coil, this one the secondary coil. So it depends which one you try to connect the source or the battery. Actually, the setup here is like, here we have the N1 and then connect with a battery. And then here we also connecting to a tunable resistor, as I mentioned. So the idea is that if we just connecting to a fixed resistor, then the current is fixed, then the magnetic field doesn't change. If the magnetic field doesn't change, this magnetic flux is not changing. There will be no induced EMF. So here we try to make it like a sliding left and right, which means that the resistance here is varying from small to large and then become smaller, become larger, back and forth. Okay, which means that this current will be changing. So as much as this current is changing, the generated B field by this inductor is also changing. So the magnetic flux here is also changing, and then there will be EMF. Okay, so the idea is like this. So here, for the primary coil, we just connected the coil to the battery, and then with a tunable resistor, we try to change the current. And then for the second coil, we just connecting to a ammeter. So this is an ammeter, which means that it just try to measure the current going through this coil. It doesn't provide any EMF. Okay, so as much as this resistance is tuning, okay, there will be induced EMF. And this phenomenon is called the mutual inductance. So previously we talked about the self-inductance, 自感应. Oh, this one is called 互感应. Okay, mutual inductance. And then similarly, if we try to connect N2 to the battery with a tunable resistor, and then we try to tune this resistor, so the current will change, and then the magnetic field will change. The magnetic flux for the secondary coil will also change, and then there will be induced EMF. Okay, so that's the idea. Okay, so the equation is only different by this one. So we use M. This M is the mutual inductance. 互感值. Okay, so the SI unit is still Henry. The SI unit is still Henry. Okay, so the only difference is that just now for the self-inductance it is E equals negative L di dt. Because we just only have a single coil, so we only need to have one current. And then this current is related to the and then also the inductance is related to the EMF, or it is nothing but the negative VL. So I always use VL equals L di dt. Here it use EMF, so just let it like this. So here for this case, I1 is the source. When I1 is changing, we multiply this M. M is the mutual inductance between the coil 1 and coil 2. Okay, so it generates the EMF at coil 2. So this is the E2. This is I1. Of course, you can also use a voltmeter. Use a voltmeter to measure the EMF here. Actually, for the experiment next week, we are using a voltmeter to measure the induced EMF value. Okay, so for this setup, we connect the source to the secondary coil. So here we have I2 di2 dt, and then from here to here is M. From here to here is also M. So for simplicity, okay, so we just have a negative M di2 dt to E1. E1 is generate for the secondary coil. So this one, E1 is the secondary coil EMF, and then here E2 is the secondary coil EMF. Okay, so here we have 1, we have 2, we have 1 here. So it depends on which one you can connect the source. Okay, so finally we have a sample problem. Okay, so let's see how far we can go. Okay, so here it says the figure shows 2 circular closed packed coil. The smaller one, radius R2. Okay, so this is R2. This is R2 with N2 turns being coaxial with the larger and in the same plane. Okay, coaxial means this one should have an axis. Axis go through the center and then perpendicular to the plane, perpendicular to the cross section. Okay, and this one this one also have a center. And then coaxial means the axis for the smaller one and the largest one are the same thing, okay, are the same axis. So they call coaxial. In Chinese this is called 同轴. Okay, coaxial. Okay, with a larger and in the same thing. Okay, so the radius is R1 and with N1 turn. Okay, derive an expression for the mutual inductance M of this arrangement of these two coils, assuming R1 is much larger than R2. We have some assumption because we need to approximate the B field generated by the larger one for the second coil. Because this is not necessarily uniform, but as much as we assume that R1 is much larger than R2, we assume that the B field across the smaller one is all the way uniform. Here you can see we have a battery here. Okay, so the larger one will generate the B field. So the smaller one will have some magnetic flux. And then if this magnetic flux is changing, then there will be induced EMF, induced current, so on and so forth. Okay, so here we try to calculate phi 21. Phi 21 means the source is from I1, generate the flux for the turn 2. Okay, so it means that it is B1 times A2. A2 is the cross-section area of the second coil, and then B1 is the B field generated by the first coil. Okay, so we have B1 A2 rather than other combination. Okay, so previously we have a L equals N phi B over I. Okay, so for mutual inductance, we change it to M equals N phi 21 over I1. We change this one. This is the definition for the inductor. And then, so this is the mutual inductance. So should be N phi 21. The source is the source is the turn 1, generate for turn 2. So this is the source I1. Okay. And then we can just plug in the value. M equals N, and then B1, plug in this one, B1A2 over I1. And then for equation 2926, we have a B of Z equals mu 0 I R squared over 2 R squared plus C squared to the 3 over 2 power. So this is for the when C equals 0. So this is the case here when C equals to 0. So we have this expression. This expression is a coil. We can calculate the B field generated at the axis. Okay, actually this is not uniform for different plates. So as much as this has a radius, but here we assume that R1 is much larger than R2. So we just assume that the B field is uniform. B1 is uniform over this whole cross-section area. And here, as much as they are in the same plane, which means that Z is equal to 0. So as much as they are at the same plane, PLA, same plane, PLANE, okay. So Z equals to 0, which means that a B of 0 is mu 0 I, and then over 2R, Okay, so here we try to change the variable so that here we should have B1 is mu 0 I1 over 2 R1, okay, rather than having I and R. So we have I1 R1, and then don't forget we have N1 turn here, so we need to multiply by N1 because we altogether have N1 turn. Okay, so here we can just plug in this expression to there. So we have M equals I think this one should be N2. This one should be N2. This one should be N2. Okay, so this one should be N2, and then B1 should be N1 mu 0 I1 over 2R1, and then we still have A2 and then I1. Okay, so here we can see that we can actually cancel this I1 and I1. Okay, so the expression here is like M equals and also we can have A2. A2 is an unknown, but the known value is R2. So this A2 should be pi R2 square. Pi R2 square. Okay, so finally we should have this one is mu 0, and then we have N1, N2, and then we have a pi R2 square over 2R1. Or we can just rearrange it like a pi mu 0 N1 N2 R2 square over 2R1. Okay, so maybe we just stop here today.